Hello once again to all my viewers for a new video, and this time it's on the third law of thermodynamics, the last axiom in the axiomatic field of in the axiomatic perspective of thermodynamics. And this one is a very quick one, so we will not be spending that much time exploring its consequences, but it basically in one sentence it would just mean that the third law fixes an absolute scale for measuring entropy. But before that, we can do a bit of a recap. From the second law of thermodynamics, we got the definition that was given by Clausius, which is basically that since we had a problem with the heat energy being a non-state parameter and T being a state parameter, he defined then the entropy as a state parameter with a ratio between the both, and where we also saw that if the change of entropy is equals 0, then the process has to be reversible, and if it is bigger, if the change gets bigger with time, then it is actually irreversible. But there cannot be any situation where the total entropy of a closed system would go would change in the negative. That is actually not possible, right? And exactly now, as we told before, till now we only had relative entropies, so we always saw like a difference of entropy, and since now through Clausius's definition we know that entropy would be a complete state parameter or state variable, so we have to also set an absolute scale for it. So to set the absolute scale, the German physicist Walter Hermann Nernst, he was actually born in Poland, but back in the days I think that region was also under the German Empire, the Prussian Empire, so he's also considered German. He formulated the third law of thermodynamics in 1905, which basically fixed an absolute scale for the entropy that could be measured. He also used then the concept of absolute zero from William Thomson, Lord Kelvin. Right. What his statement was basically that the entropy of a system, it tends to go for very low temperatures, which reach around absolute zero, to a constant value, and let's say that it is S0 for entropy at 0 Kelvin, and he basically set this constant value as 0. So basically S0 is 0, so that one can work with absolute scale of entropy. Right, it's not really that difficult, but and also it is it seems very trivial to us as readers, but we have to also keep in mind that in axiomatic thermodynamics, as the name suggests, the axioms are very, very important, and this was again very important in order to fix the absolute scale for entropy, or else we would have to always work with relative entropies, which might not be always the most efficient way to work with. Right. Another implication from Clausius' theorem, which we got from the second law of thermodynamics, which could be added also, is that let's say like from point A to point B, that there's a process which is P, and there's also a process which is the reverse of it, which is R bar. When we want to write the entropies of both, you can see that one goes from A to B, that is the process P, and the other goes from B to A for the process R bar. And since we know from integration rules that when we want to swap these two boundaries, then we basically do it with a minus, like we change the plus into a minus, and that is also what we did. And again, for entropies in general, this should be then less than equals 0. Right, and so that's about it. Hope you liked the video. I will be bringing again new concepts to finish off the axiomatic thermodynamics as soon as possible. The axioms for now are done and defined, and now we'll look forward into exploring energy and entropy as potentials for like different potentials in general for axiomatic thermodynamics. So if you like the video, please press on the like and share with your friends. And if you also have any constructive criticism, please let me know in the comments below. Thank you.